Okay, I have a lot of time, but I do not think that I will speak so much. Okay. My topic is statistical inference for the generalized Ornstein-Uhlenbeck process, and I would like to start my talk with a very short historical overview of this topic. Actually, the Ornstein-Uhlenbeck process appeared as a model for describing the motion of a free particle in a fluid. So Albert Einstein, in his famous work 1905, suggested to describe this motion by Brownian motion. And 25 years later, Ornstein and Uhlenbeck suggested to add the concept of friction in this model. So using modern language, this means that the velocity of a particle with mass m can be described by a stochastic process Vt, which is a solution of the following stochastic differential equation. Do I have a stick here? Question to organizers. Okay, I will ask myself. Okay. If we take lambda equal to 0, of course, we get the original model by Albert Einstein. Really, yeah. And lambda is called a friction coefficient. Bt is a Brownian motion in this equation. This equation is known as Langevin equation. It allows for closed form solution. It's written here. And in 1989, De Haan and Karandigar introduced the so-called generalized Ornstein-Uhlenbeck model. This model, of course, is a natural generalization of the model by Ornstein and Uhlenbeck, and is used is described via some two-dimensional Levy process xi eta t. There are two essentially different. Thanks a lot. Two essentially different partial cases of the generalized Ornstein-Uhlenbeck model. The first one is characterized by the fact that the process xi t is not stochastic, but proportional to time. And the process eta is, in fact, any Levy process, one-dimensional. This partial case is known as Levy-driven Ornstein-Uhlenbeck, and statistical inference for this kind of processes was considered many times by different authors. So some colleagues from the Weierstrass Institute are still writing papers about this. And another case, which is the object of interest in our research, is the case when xi can be any Levy process, and eta is actually equal to t. I do not know special name of this process, so it appeared in many contexts, but sometimes it is called generalized Ornstein-Uhlenbeck, but I do not know a specific name for this partial case. The point is that the process xi t in this case is a solution of the following stochastic differential equation, where ut is some Levy process which can be explicitly defined by the process xi. Since there is a word econometrics is the title of this conference, I would like to give some motivation from econometrics of this model. So if we start with the famous arch model, autoregressive conditional heteroscedastic, so we can come to some continuous time model, which actually uses the generalized Ornstein-Uhlenbeck process. So how it is done? So the arch model is well known. The simplest case, can be defined as follows. So the returns are the product of two discrete time processes. The first one is standard deviations, which linearly depend on previous values of this process. And epsilon 1 is a so-called white noise process. It has zero mean and unit variance. Any questions? Questions? Okay, this process was generalized many times. The most popular generalization is called Garch model. This model, sigma n squared, is proportional, linearly depends not only on the previous value of the process y squared, but also for the previous value of the variance. And what is also quite well known that the Garch model captures many so-called stylized facts of financial data, like heavy tails. So values are uncorrelated but not independent. Stochastic volatility is stochastic, and so on. How to define, the question is how to define the process in continuous time, which will also capture off of these stylized facts. And the answer was given by Uhlenbeck, Linear, and Mahler about 10 years ago. This model is called continuous Garch, co-Garch. And the general idea is quite simple, to replace epsilon y by the increments of some Levy process xi. This idea leads to introducing the following model with the stochastic integral. And as you can see, sigma t is exactly the generalized Ornstein-Uhlenbeck process in our meaning of this word. So when one of the process is proportional to the time, and the second one is as a Levy process. Next, I would like to give a couple of references, say a couple of words about the most important properties of the generalized Ornstein-Uhlenbeck model. The first property is stationarity. It is proven that there is a stationary Cadillac version of this process, and the stationary distribution is given by the distribution of the exponential function. So a couple of years ago, I gave a talk at our previous meeting, Premolab meeting in Berlin, where I talked a lot about the application of such objects. But here is a short list of these applications. Actually, this was one of the topics of Mark Yor, so he wrote an interesting book about this. And there are many applications in financial mathematics, first of all. So this object plays a crucial role in pricing of Asian options. Next, there is one model which is called carousel system, which is widely used in modern warehouses. And exponential functional is an asymptotic distribution of the minimum time which is needed for the picker to pick up all elements of this warehouse. Many applications in crystallography and astrophysics in the context of models where some big object splits into pieces over time. And this process can be described by some self-similar rules. This is called self-similar fragmentation. Also, some applications to modeling TCP/IP protocol, the most important protocol of the internet. So there is some connection with information transmission problems, and actually these authors, Vladimir Panov, are the employees of France Telecom, and they try to use these models in practice. And also there are some physical interpretations. The main reference here is a dissertation by Montus. So if you would like to know more about stationary properties of the generalized Ornstein-Uhlenbeck, I advise you to read some parts of the dissertation by Anita Beme, which is completely devoted to such properties. Second property of the generalized Ornstein-Uhlenbeck is the so-called mixing property. I think that it's more or less well known, but I will say a couple of words. So if we have two sigma algebras, beta and c, then we can define a couple of coefficients which describe the dependence between these sigma algebras. The most well-used coefficients are alpha and beta mixing coefficients. So they are defined here. So B belongs to the first sigma algebra and C to the second. And this concept can be extended to a sequence of random variables. So if we take two sigma algebras. One sigma algebra is generated by all elements of this sequence with numbers less than t, and second sigma algebra is generated by all elements which have numbers larger than t plus k. We can compute the alpha mixing coefficients between these two sigma algebras and then take the supremum over all possible t. If these coefficients alpha k are tending to 0 as k tends to infinity, then the sequence is said to be alpha mixing. And moreover, if it tends to infinity at exponential rate, it tends to 0 at exponential rate, then the sequence is called exponentially alpha mixing. So similarly, we can introduce beta mixing coefficients and exponentially beta mixing if we simply change the letter alpha to the letter beta. So since doubled alpha coefficient is less or equal than beta, then from exponentially beta mixing it follows exponentially alpha mixing. In this theory there is one inequality which is quite useful for practical reasons. This inequality is called Davidov's inequality in the honor of Yuri Davidov, who was the guest of our laboratory for a couple of months ago. And this inequality reveals the main reason why we consider alpha and beta coefficients. Actually, we can upper bound the covariances between random variables belonging to sigma algebras if we can say something about the alpha coefficient. So more precisely, if we take two random variables, gamma 1 and gamma 2, then it turns out that the covariance between these two random variables is less or equal than some object, where alpha is actually the alpha mixing coefficient between sigma algebra generated by gamma 1 and sigma algebra generated by gamma 2. And what was proven in one paper by Fazen, 2010, that the generalized Ornstein-Uhlenbeck process is exponentially beta mixing. Therefore, we can use this theory for proving some theoretical facts, which I will describe later. Well, I would like to get closer to the topic of our research, to statistical inference for this model. But before I will formulate the problem and tell you the idea about our approach, I would like to say a couple of words about the Mellin transform, because this transform will play a crucial role in the following in what follows. Okay. So the definition is quite simple and very close to the definition of the Laplace transform or Fourier transform, but there is one essential difference. So the argument of this transform is actually complex. Therefore, so this fact is the origin of some technical difficulties. And I would like to say a couple of words about the main properties of the Mellin transform. So actually, under some mild conditions on the function f, the Mellin transform is analytic in some region. So this region is actually a strip, which is called the strip of analyticity. But for most cases, a Mellin transform is also at least meromorphic outside the strip. So there are a couple of facts that are analogs of similar facts in the theory of Fourier transforms, like Parsenval formula or inverse Fourier transform. And the main difficulty here is that we should take a complex integral over some contour, and this contour should be found in quite sophisticated way. It should be taken such that all singularities of the functions f and g are on the one side of this contour. So I will skip these technical details, but so these facts are still true for the Mellin transform. What is really needed for our method is one specific property of the Mellin transform of exponential function. This specific property is the following recursive formula. Here we denote by f the Laplace exponent of the process xi. And z is a complex value, is a complex number which can be taken from another strip, from which can be explicitly found. This recursive formula was firstly proven by Maulik and Swart, but their proof is valid only for real zeta. And later, 5 years ago, it was proven by Kuznetsov, Pardo, and Savov, exactly the same formulation as it is written on this slide. Why do we need this formula? Because it allows us to estimate the Laplace exponent of the process by the Mellin transform of its exponential function. And as you will see later, this gives us an opportunity to estimate the parameters of the process xi and to completely recover the Levy measure of this process. Now I'm ready to formulate the setup of our study. So at this moment we can forget about the generalized Ornstein-Uhlenbeck process because we will assume that it is stationary and has mixing properties. And we can think about this problem in the following way. So we have some observations of the exponential function. For simplicity, we will assume that the Levy process xi is actually a pure subordinated with finite Levy measure. So this means that mu, first element, is positive. Second element of the Levy triplet sigma is equal to 0. And the Levy measure possesses the following properties. So it is 0. It is 0 on the negative half line, and it's finite on the positive half line. So we suppose that we are given by some observations of this exponential functional, and we aim to estimate parameters lambda, mu, and to recover the complete the Levy measure mu by the observations of the functional. Estimation procedure has 4 steps, and I would like to explain shortly all of them. So the first 2 steps are quite simple. We estimate the Mellin transform by its natural empirical counterpart. This empirical counterpart has the same wonderful properties as empirical characteristic function, for instance. And next we use the recursive formula for the Mellin transform for estimation of the Laplace exponent. Third, we're able to estimate the parameters lambda and mu. And the main motivation for the procedure, which I describe here, is one representation for the Laplace exponent. This representation is written at the beginning of this slide. And actually, it directly follows from the famous Levy-Hinchen formula. So here, we take complex argument for the Laplace exponent, and we fix the real part of this argument. It is denoted by U circle, and change only the imaginary part. And if we are doing so, then the characteristic function at this point actually is the sum of 2 elements. So the first is a linear combination. The first part is actually a linear function of v. And the second one is nothing more than Fourier transform of the measure nu bar taken in the point minus v. A well-known Riemann-Lebesgue measure tells us that the Fourier transform tends to 0 as the argument tends to infinity. Therefore, for large v, the Laplace exponent is actually proportional to v for large v. And we efficiently use this idea and define the estimate of the parameters lambda and mu as a solution of the following optimization problem. Here, the weight function Vn of v is constructed such that only big V are playing some role in this minimization problem. More precisely, we take Vn in the following form, where the sequence Vn is tending to infinity as n grows, and W of V is actually a function with finite support. It is worth mentioning that this optimization problem has a closed form solution, which is written here. And as you can see, the forms of these solutions for mu and for lambda are very close to each other. So it's some integral over weighted function product with imaginary or real part of the empirical Laplace transform. The only difference in this weighted function, in the first case, it can be represented as Vn in the power -2, product with something that is bounded. And here this is minus first power of Vn. So if we already have estimates of lambda and mu, we are able to estimate the Fourier transform of the measure bar nu and to recover the Levy measure. The main motivation for the estimating procedure is exactly the same. So we once more use this representation for the Laplace exponent and read this formula a little bit in another manner. So we put the Fourier transform on the left-hand side and everything else on the right-hand side. Actually, all elements of the right-hand side can be estimated. We already did this. And therefore, we can estimate the Fourier transform of this measure and then using the Fourier inversion formula to recover the Levy measure. So what we can prove for this model? Actually, the crucial role for theoretical properties plays the asymptotic behavior of the Mellin transform when the imaginary part of its argument is tending to infinity. And in most cases, we have two different behaviors of the Mellin transform. So polynomial behavior and the set of the corresponding densities pi we denote by pi, capital, okay, p. And the second case when the Mellin transform behaves exponentially. And this set we denote by E. Later I will show you the results. So they're essentially different for these two kinds of behavior. And we also introduce a couple of additional assumptions. But what is the most important is the behavior of the Fourier transform. This condition seems to be a little bit artificial, but we can prove that in all our examples this condition fulfills. And actually, in some cases we can consider much more weaker condition about the s derivative of the Levy measure. So actually from this condition on the Fourier transform, it follows that the derivative of the Levy measure is finite. So, but sometimes we can use the condition on the derivative. The condition is weaker, but it's enough for proving many facts. So the first result is the upper bound for our estimates for lambda and mu. As I told you, there is additional essential difference between two behaviors of the Mellin transform. So the first case when pi belongs to the family capital P. In this case, we have the rates of convergence, so they are rather polynomial. And as you can see, the rates of convergence are very close to each other. The difference is only in one number. So here's 2 and here is 1. This is not surprising because, as I told you, we get that the final estimates for these two parameters are very close to each other. The difference is only in the weight function. And if pi belongs to the exponential family, then the rates of convergence are logarithmic. And we think that these rates cannot be improved.
This sign, what does it mean?
This sign, up to a constant. So for large n, this is less or equal than some constant product with logarithm. As for the quality of our estimator for the Levy measure, we use one additional assumption on the kernel K. So actually, this assumption is well used in the famous book by Alexander Tsibakov, and we borrow some ideas from his book, as many our colleagues. So, what we can prove is that the MISE, so minimal integrated squared error of our estimator, is also of polynomial order if we consider pi from a polynomial family. And in the second case, it is also logarithmic. And you can see that the rates of this convergence are very close to the rates of convergence of lambda and mu. So some simulation examples for our theory. So we consider two examples. In the first case, so pure jump part of our process has a Levy density in the following form. This is exponential distribution. And in the second case, pure jump component is actually a compound Poisson process where the distribution of any eta k is a truncated normal distribution. It can be shown, easily shown, that the exponential functional in this case can be decomposed in such series. So on the first two steps, we try to estimate the Laplace exponent in complex points. So for our first example, so exponential distribution, we actually obtained that our methodology works very well. So you see that there is some difference in the real parts of the true value and our estimator. But if you look at the xy, you see that the difference is very small. Imaginary part coincide fast perfectly. And if you take absolute values, so it's also almost perfectly estimated. For our second example, the situation is also very good. So pictures differ from the previous case, but the overall resume is exactly the same. So absolute values of our estimators are very close to the absolute values of the true value. Next, we are trying to estimate parameters mu at lambda. Here is some illustration. So box and whiskers plot. For the first case, I guess. Yes, and we get that actually our procedure works very good. So already at n equal to 10,000, our convergence become very close. So our estimator become much closer to the original value.
That's shown here, the absolute values of the errors, or what
No. So the true value, so C and A is a misprint, of course. C is actually mu and A is actually lambda, okay? On the left picture, we're trying to estimate, so this picture illustrates how good we estimate the parameter mu. True value is 1.8. And this picture shows us how good our methodology works if we change the number of observations. So this is 1,000, 3,000, 5,000, 10,000. And what we can check using this picture that our estimator seems to be converge. So our estimator converges to the true value. So this picture gives us a hope that our estimator converges to a true value. What I was going to say?
Was the problem how to choose the smoothing parameter, the VM, the
Here Vn is of course fixed. Fixed by, but it is
No, but I mean,
large enough, but it is fixed.
Fixed or tuned?
Tuned by hand. And the last picture, how good our procedure estimates the Levy density. Here we have a very interesting problem. So we're trying to estimate a real valued measure by a complex estimator. In fact, on the right-hand side of this formula stands something which is complex. And we're trying to estimate a measure which is in fact real valued. But it turns out that the imaginary part of the right-hand side of this equality is very, very small. So it is 10 to the power minus 18. And therefore, we can skip the imaginary part and hope that our estimator works also quite well. So actually, the real parts are given on the left picture. Maybe this estimator is not perfect, but if you look in the literature, so you cannot find some pictures which are better than mine. So normally, the quality is much worse. The quality of the estimator for Levy measures.
for this problem, there is no literature.
But there is some literature about the estimation of Levy measure. Your article, for instance.
No, but I mean, for this problem particularly, you cannot compare with some.
I can compare with other pictures on the same spirit.
Okay.
There are some pictures on the same spirit, I would like to say. Okay. Finally, I would like to ask one open question. So let us consider our model with the following parameters. We take Levy measure as exponent to the power minus bx, product with x in the power m. This example works very good with our theory, but we're trying to know more about this model. And actually what we can prove, and what is actually proved in the paper by Kuznetsov, is that the Mellin transform of the exponential function for this model has the following form. So here j of x is this fraction, and gamma stands for the gamma function. So we know all about the Mellin transform. So these zetas are explicitly known. These are solutions of the following equation, non-zero solutions. And what was a surprise for us is that this family of distributions is already known in the literature, and they are called Dufresne laws. It was appeared in the paper by Chamayou and Letak in 1999. And the question which we would like to ask, and which is from our point of view a little bit difficult, is how to find the density of the exponential functional for this case. So we know the Mellin transform of the exponential functional, but how to find the density, or at least how to find the asymptotic behavior of the density. This is also important for our theory. To the best of our knowledge, this question is open in the literature, and I guess that this can be a good topic for further research. But at the moment, that is all. I would like to thank you for your attention.
Thank you, Vladimir. Questions?
Yes.
For your first result for the L2 norm,
Yes.
there was a logarithmic factor. And I mean, for an L2 norm, this is
Logarithm.
you have not a log factor here.
Here.
This is counted somehow.
You mean that here we have log and here we have no log?
Can you explain this? Why there's a
There is a methodology by Econometrics, don't take care about the logarithm.
I mean, because typically it is if you go from L2 to subnorm, then you have.
But in fact,
or is maybe it is
the
some
point
boundary
is,
effects or.
here the logarithm is because of maybe a little bit rough estimate in the case of dependent data. So because this result is not quite correct. This result was general for dependent data, alpha mixing. But if you have independent data, you don't have this logarithm. We don't get. But if you have dependent data, then maybe the estimate a little bit rough, maybe another inequality should be not this Davidov inequality.
You are sure that there is a log, or it is you have no log?
No, I'm sure that should not be log. I think here, especially some dependent data, I think there's no usual, there are no log, yes? At least in low bound, we don't have log. We have two low bound, there are no log.
So maybe the problem is that we use Davidov inequality, as Denis said, and there are some more strong results like Remus inequality. Maybe if they consider this more detailed.
But I think it's not about inequality only, but it's about with blocking. You have to block, make blocks, dependent data to make them independent. You know this methodology. And then of course it's a question how you should block. So at least you can win in the power program.
Some dependent.
No, we alpha mix.
I don't believe that this additional outcome comes from Vladimir inequality, because usually even with some of these other estimated programs is bounded, because usually the of these other estimated exponential orders or something like that. But maybe somewhere in the procedure you move realizing some other estimate or in some and maybe in some earlier stage what this log time for I don't know.
Maybe this result is
Any more questions? Okay, if not the case, then let's take all the speakers.